Hi everyone, thanks for coming, welcome. This will be a little more light on the maths than some of the other presentations here, which should be good. There's a intermezzo just before the break, or goûter, as we say in French. Who I am, really quickly, I'm Lancelot. I'm co-founder and CTO of Hyle. We're building a blockchain network targeting provable applications or ZK apps. What I'm going to be talking about is what we're doing, but it's also what we think will happen anyways. I was previously working in the Starknet ecosystem on an NFT protocol called Brick. You might know some of that, which was my introduction to zero-knowledge technology and validity proofs and things like that. What I'm going to be talking about is what we think will be the future of dApp and smart contract development, thanks to zero-knowledge proofs, and both the impact this will have on applications and on blockchains, because I'm talking about a blockchain context here. So let's do a quick thought experiment. Let's say it's 2030 and you want to write an on-chain game. So let's quickly answer the question, why would you go on-chain? I usually stray away from answering that, but there's a few good reasons why you might want that. Maybe you want the censorship resistance. Maybe you want the composability and the liquidity access. Maybe you want to use the blockchain as a distribution network. And a few other things that are legitimate, but those are like the three main big ones. So if you want to go on-chain, still, because it's 2030, you don't want to think about cold data size or gas costs and all that jazz. You shouldn't have to think about that in 2030. And because you're making an on-chain game, you want to have low latency. You want it to be about real time, you want it to feel like a game. And because it's 2030, maybe somehow the metaverse is hype again, and you want people to own an NFT to be able to play your game or something. But maybe you don't want them to have to show which NFT they're using, so you want privacy. And with privacy, you'll have to use zero-knowledge proofs. So you have a proof of concept of your game written in Rust, so you'll want to use one of the ZK VMs that you can run Rust on. There's a bunch of them, but because it's 2030, you can use SP2 or RISC-1. I couldn't find a good wordplay for Nexus or Valida or Jolt or any other ones. Leave a comment below if you find one. That's for YouTube later. Yeah, so you're writing your application. How do you put it on chain? Well, our argument, our thesis is that applications and rollups will become interchangeable, as in both will be the same thing, essentially. Rollups are apps, and apps are just rollups. In that model, transactions, so blockchains are just state machines. You have a state, you send a transaction that operates a state transition to a new state. Rollups just take that and apply ZK or validity proofs, depending on the context of that. Essentially, your transactions are just proofs of a state transition. So you have, you have an initial state, that's like the green blob, let's say, and that's just a state commitment. It's like the iceberg thing. It hides that most of the data is not necessarily stored by the chain, but it's there. You just have this commitment. And all of your transactions are just state transitions. So you go from the green state commitment to the blue state commitment to the red one. And every time there's like an underlying database that's full of information that you don't really need to know about to know that the information is secure, because you have a ZK proof that there is a valid transition according to your application from the green blob to the blue blob to the red blob. The key thing here is that those are ordered, and of course you need to know some information about the program to be able to verify the proofs. So depending on the system, that could be a verification key, an image ID, a bunch of other things. How do you generate the proofs? In 2030, you'll have a few options. You'll be able to do client-side proving. If you have access to the code of the application, and you have access to the state of the application, because all of that is open source or widely distributed, you can just generate your proofs on your own computer because it's fast in 2030. Or you can do a small computation locally, and because the application you want to use is huge, even though it's fast, you want to send the rest to a centralized server, to a B2B app that wants to do their own thing with it, to a SaaS, essentially. Or you'll want to leverage a proof of market of some kind where you just say, well, I have this thing, I want to generate a proof, and people do it for you, and you pay them for that. And then the proof just gets sent to the chain, and we, act the state transition. Once the information has been sent to the chain, of course, you'll need to read it, you'll need to see it, and for that, you'll need to index the information. Again, this is pretty straightforward to do. You have a bunch of options, but the two big ones will be that either you'll read the information yourself on the chain and reconstruct a local database that you see of the app information, or you'll have to rely on the dApp server to do it for you because they're doing their own indexing. But it remains trustless even though they're doing it, because they can prove to you that the information they're showing you matches what's on the chain. So that's a Merkle inclusion proof or something like that. That's like the whole property, of the data integrity security provided by the chain, and you have the iceberg within the app infra. So quick recap, transactions as proof of state transitions, dApps are just verification key and state commitment or state root. Users can prove client-side or use prover services, and chains don't store the data, but guarantee its integrity, which is much better because blockchains are terrible at storing data. And thankfully, indexation remains trustless. Now let's end the thought experiment and think, well, why not do it right now? It's 2024, and you might write an on-chain game. Well, you'll have a reality check happen pretty quickly because there's a few problems. The first is how do you do composable contract calls easily? The second is that because it's 2024, proving time and proving time latency are a big issue. And the third is parallelization. Let's get the simple one out of the way. To give an example here, you want people to own a CryptoPunk to be able to play Tetris. I'm not going to say why, because there's really no reason to, but why not? If you are trying to do this conventionally, you'll have to use recursion. Essentially, you'll have to embed within your Tetris game the verification of the proof of ownership of a CryptoPunk, and I don't know, that might be like storage call on Ethereum or something. It's kind of important. But the basic idea is that if you want to change that, or if you want to change the CryptoPunk contract, you'd have to update your Tetris contract because the two are embedded together. You can't change one and not the other and things like that. And also you need to be able to verify the proofs. So that implies that you're doing recursion, which can be slow, complicated, this type of thing. What we think will happen in the future and what we're offering at Hyle is actual composability, where you have two separate proofs within the same transaction. And you have the proof that you own a CryptoPunk, which is doing its own thing. And then within the Tetris proof, you essentially say, oh, protocol, can you check that there's also a proof for the ownership of a CryptoPunk? And the protocol will do the check separately. So it's essentially like in a functional programming context, we're pushing the side effects to the end of the computation, and we're just verifying that things seem to match at the end, instead of doing it along the way in a more linear pattern. So that's the easy thing. But to take another example now, which might be a bit more realistic, you have an auction. The auction is ending at this point. That's my red bar on the timeline. Let's say you see the auction, you want to bid, but by the time you generate your proof, well, the auction's ended because, I don't know, it was terribly written and it took several hours to generate the proof. Well, of course, you're sad because you couldn't bid. Or, and this is an even worse problem, maybe you saw the auction and another guy did it at the same time, and at this point you both observe the initial state commitment of the auction contract, which is this green state. You both craft your transaction. They're both state transitions from this initial start state that's green. The guy on top is blue. You end up on a red state. The guy on top is faster than you because he's got a better computer or something. He sends his transaction first, and at this point, your transaction will necessarily bounce because the proof of state transition no longer applies. I don't know if I can go from blue to red, so I just don't know what to do, and I have to reject your transaction. And again, you are sad. There is, thankfully, one solution to both of these problems, and this is what we call delayed proving. Essentially, it's like if you go to a restaurant, you can make a reservation, and you can always, claim the table when that time comes. Both you and the other guy see the auction contract. You send the blob some piece of data defined by the application, the auction contract, and that arrives on chain immediately. And then essentially you have some more time to generate a proof that this transaction was indeed correct. that you indeed have the money to bid or some other requirements. The good thing here is that once you've sent the 2 initial transactions, they're sequenced, and so you can observe that you'll need to craft the second one, the proof, based on top of the blue state, not the green state that you initially saw. So you can generate the proofs based on the correct state, and you won't have this parallelization problem, and you, again, won't have the timeout problem because you don't need to wait for the proof to be generated to be able to send it to the chain. So you can just claim the spot, start generating the proof once you know that you're good, and well, both of you won't be happy, I guess, in the case of an auction, but you're still happy because you managed to send the chain, to send the transaction to the chain and do your thing. So if it's 2024, but you're using Hyle, well, you can do something that's, I don't have a word for it. I wrote permissionless rollup mode, and I don't like that. But essentially, you want low latency, as I said earlier. So what you're going to want to do for a game is make something that's peer-to-peer. Your players amongst themselves are building a consensus almost in real time. That's something that, for example, the Playment team is building towards. And occasionally, you want to send some side effect to a blockchain because that's where you want to tap into that liquidity. So I don't know, you won a game, and so you should earn some reward or something. You just build your consensus amongst yourselves, and occasionally you send that information to the chain. And you have plenty of time to generate your proof, even though it's really complicated because this is a video game, and even though it's usually would be latency dependent, because we've moved proofs out of the critical path of blockchain interaction, essentially. And yeah, this is good also because in terms of gas costs, well, the chain is doing very little. We're just sequencing the information, providing a little bit of data availability because we need that, and settling by verifying your transactions. So we call that a lean blockchain, basically seeing blockchains just as custodians of data integrity, thanks to zero-knowledge proofs, instead of I don't know, the old view of the world computer, just providing sequencing, a little bit of data availability and settlement. And thanks to stuff like delayed proving and native proof composability, you have high performance, the same level of programmability that you would have on Ethereum or any other regular blockchain, except you're not interacting with 5 blockchains like you would if you were using different layers for all these things. It's all happening in the same place. So if you want to try this thing out, you have some cool idea for provable applications, you can talk to us. This is the QR code for our Telegram. Or you can come talk to us in person, well, today, of course, or tomorrow at our fancy petit déjeuner, which we're organizing pretty close by. Yeah, and we'd be happy, of course, to have you and talk what we can build. That would be cool. Thanks for coming, and I guess I have some time for questions, maybe.
Absolutely, but give me a hand first.